Alright, tonight I'm recording for the January 15th class. We're already halfway through January, and we want to start today with a very serious question. What do you do with a dead chemist? Well, what else is there to do but to bury him? Alright, we're actually going to review Chapter 6 and reminding y'all that we are having a 50-point quiz next time y'all come to class on Thursday. Of course, our quizzes are normally 30 points, but there's not enough to really make a test and a quiz, so we're just going to knock it out with a 50-point quiz. All right, so without further ado, let's jump on in to our review and try to do a good job with the camera here. All right, so let's remind ourselves what we are trying to accomplish in this chapter. Describe the central theoretical problem addressed by Vesper theory. Distinguish between domain geometry and molecular geometry. That's that long table there, and we'll kind of go through what you guys are expected to know there. Use the Vesper theory to predict. We've done a good bit of that in our homework. State the names, be able to name those same things. The conditions, I don't know how you'd predict anything if you don't know the conditions that they form, or maybe he's talking about metals there, I'm not sure. We're mostly going to be worried about, I'm going to give you a compound and you're going to figure out what its Lewis structure is and then what its Vesper structure is. Explain how non-bonding electron pairs apply the Vesper theory and the principles of electron domain geometry to describe the geometries and bond angles of larger molecules. We haven't really focused on that a lot. There may be a question or two on it. The same rules apply, and we'll go through some of that. Discuss metallic bonding, compare and contrast covalent versus metallic. Talk about close packing, talk about why they're good conductors, hydrogen bonding, and then the van der Waals forces. Okay, and so I'll kind of try to swap between my notes and try and get this up as high as I can here. I need to put the camera up one. All right, so things to know for the quiz here. We want to know what Vesper stands for. Let's say what the acronym stands for. That's backwards, NIM. And of course, valence shell electron pair repulsion. Okay, that's that those lone pairs cause those molecules to form in certain ways, as if there was an extra atom attached there. Okay, and we want to talk about electron domains versus bonding domains, and that's we want to know what lone pairs are. Okay, and non-bonding domains. Okay, so if we've got our let's do just water. Okay, we end up with a bonding domain and a non-bonding domain. Okay? And so obviously you'd want to be able to, once you drew a Lewis structure, be able to label each one of those should you be asked to do that. I haven't written the quiz yet, so I'm not exactly sure how that's going to look on the quiz, but you need to be prepared for that. All right. So just kind of, if these italicized words, you see them in a chapter, you need to know what they are. Okay. All right. So just kind of in order, then we've got our linear, which is very easy to remember. Trigonal planar, it's in a plane and there are 3 sides. Trigonal. Okay. Tetrahedral, it's got 4 things bonded to a central. Okay. And that's our angle there. Okay. Yeah. Well, let's just roll through these and then we'll think about how many of these angles we're going to actually need to know. Okay. Trigonal bipyramidal. Okay, so that's a super fancy word, and I remember it being very stressful for me in high school. But there's really no reason why it should be there. It's trigonal. Okay, like a triangle. Then bipyramidal. 1 pyramid, 2 pyramids. Okay, so there are 2 pyramids. Yeah, it's too close to the camera there, but there are 2 pyramids like that. And then these are the 1, 2, 3 points that are formed here. Okay, so trigonal, remember that, and then bipyramidal. All right, and think about these angles here. Okay, there's 360 in the circle. It's 1, 2, 3 of them. Gotta be 120. They're even. Okay, and then think about this sticking up straight at a perpendicular angle to the plane that's through here, and of course it's got to be 90. So there's really no memory thus far other than this guy right here. Okay, 180, duh, it's a straight line. 120, 1, 2, 3, 360 divided by 3. This one you need to memorize, I guess, 109.5. Sorry, 109.5. Okay. This is, again, common sense. 120, 120, 120, 90. I'm not saying everyone would figure this out, right? Like I told you, it was stressful for me in high school as well. But I'm showing you the logic behind it. So once you think it through, it should not be that big of a deal. And then the octahedral is 90 on all angles there. Okay? All right, and then of course we look at the bent geometry right here. Okay, and it's the same as the trigonal planar up here, except this guy goes away and is replaced with a non-bonding lone pair of electrons. Okay, let's refresh ourselves on what this table is here. All right, so AB2, there's an A atom and 2 B atoms. Doesn't matter what they are, right? This could be any number of things in here. Of course, there are only certain ones that are going to form that way, but any one that form that way will look like this. Okay, so you got 2 bonding pairs, 1, 2. And no non-bonding pairs. Okay, linear and linear. Okay, boom, we see that. All right, AB3, 1, 1, 2, 3. Okay, no non-bonding pairs. They're all bonding pairs, which just means there's an atom there, right? Okay, trigonal planar, BF3, no problem there. Nothing to see here. Okay, electron domain geometry and molecular geometry are both the same. Okay, now let's look right here. AB2E. Remember what this means. It's got two atoms bonded to one atom and then a lone pair, AB2E. Okay? Two bonding pairs and one bonding pair. This is just restating what this is right here. Okay? So trigonal planar, same as this one. Okay? But then when we look at the actual molecule itself, we stop looking at the lone pairs for this one, and we see that it's bent. Okay, so if we had a space-filling model, we would have it drawn like this. Okay, and it would be bent. Okay, and if we knew everything about it, we knew that there would be a lone pair of electrons up there. But as far as the actual space filling of the molecule, we actually are just looking at a bent one right there. Okay? All right? And so we just need to be aware that now that one is a little bit different. All right? AB4, tetrahedral. Okay? One molecule in the middle, 4 around it for a total of 5, and that is that baby right there. Okay? No problem. Don't be thrown off and think that this is all in one plane smushed down like that with a C and then H's around it. It's not what it is. It's this. Okay, that Lewis structure is there for conveying certain information. It's not there for geometry. That's what this is for. Okay? This is just to tell you what's bonded to what and with how many bonds, single, double, triple, whatever. Okay. All right. Then we've got the AB3, and we've lost one of the B's. It's gone from 4 down to 3, and it's been replaced with a lone pair. We see the difference there. Okay. And why is it trigonal pyramidal? Because that is got an N sitting up there with one thing of electrons sticking up from the top and then 3 H's below it. Okay? The shape is tetrahedral just like this one, except one of these has been replaced with an electron set. Okay? We see that right here. Okay? Then we replace a second one with an electron set, like we just talked about with water over here. And it's still tetrahedral, okay, but now it's just bent. Okay, so again, if we would draw this, now in this case, we would have a second set of electrons. Okay, but the molecule is still bent. So if we were just to look at this under a microscope, of course, we don't have a microscope that can actually see molecules individually, but we would see from various indirect chemical evidence that these have a similar shape. So even though he's only got a trigonal planar, he's bent. Even though he's tetrahedral, he's bent. And so they're both bent in a similar way, and you can see that from the Lewis structures here. Okay? All right. Trigonal bipyramidal here. 1, 2, 3, 4, 5 bonded to the center. And trigonal bipyramidal, SB5. SF6 here is an octahedral. 1, 2, 3, 4 around that center one, and then 1 on the top and the bottom, such as this. Okay, and that is same. Okay, so same. A little bit different on the bent. A little bit different on the bent. Okay, so 2 of your ones that are different are on the bent. And then your only other one that's different is your trigonal pyramidal one from the tetrahedral. Okay, So I don't want you guys to spend 100 hours trying to memorize these things. I want you to think it through, and I want you to figure out how the shape came to be, and then I want you to be able to do which one of these it is, okay, which you should be able to do without memorizing. Okay, the key is not to have to memorize this. The key is to think it through, but you're only going to be able to think it through if you do your Lewis structures correctly and then extrapolate correctly from there. Okay, so it's like one of those problems when you get the first one wrong, everything subsequently is wrong. So if you don't do your Lewis structures correctly, okay, you're going to have a real trouble figuring out how many bonds it has and how many lone pairs it has if you don't do that right. Okay, so I'm not going to be super tricky with this, okay, but I'm also not going to just give you only easy ones or only these examples right here. Okay, so don't go and memorize these and think that that's all that's going to show up on the quiz. Okay, we've had plenty of practice with Lewis structures. Y'all have done it for 2 homeworks. I don't think I've gotten any emails saying, "Hey, I really don't understand this." So y'all take a hard look at what you're able to do and what you're able not to do, and let me know if you need some help. If you're confused about how to do it, I know I won't say that I was a world-class Lewis structure teacher, but I think you have a good basis in that. And so let me know if you're still confused about it or whatever, and we'll have some communication before the quiz. But it's going to be on the quiz. Okay. All right. So moving on. So clearly this is a central set of information that's going to appear on that quiz. All right. So that's not going away. Okay. Next. Okay. On bond. All right. So this is good. The effect on bond angle here. I am willing to accept. With the fact that you guys are going to have to be working through this, okay, and like I said, you're not going to memorize it, but I'm willing to accept, let's see, where is a succinct sentence here? The non-bonding domains push a bit harder than the bonding domains, okay? Where, okay, so I basically want you to know that this is less than 120 degrees, and that this is less than 109.5 degrees. Okay, you see what I'm saying? I don't need a specific number. I need you to know that this squeezes these guys in a little bit. Whereas if this was just an atom, that would be 120, 120, 120. Okay, they actually do squeeze it in. These electrons do. They push a little bit harder on these to cause those molecules to push in like a spring. Okay, so you just need to know that it's less than 120, less than 109.5, and that's true for any of the. Let's see what else. No, that's fine. Just those 2 situations, because there aren't any other geometries that result from that. Okay, and so you see right here, like this actually gets a little bit. It's got a little bit of a different number, 107 versus 104.5 on this other page over here. So we're not gonna fool with all that. Okay, you just need to know that it reduces that angle between them. All right. We just need to know that these are close packing and that these are the 2 names. Okay. So we need to know geometry and electron domain. I'm making notes for myself here, so I'd make sure I test you on exactly what I'm saying here. Domain geometry and molecular. I'm going to say everything. Page 154. Okay. All right. And then 6.1.3. All right. And then we need to know from 6.2, only know two kinds of close packing. Okay. And we need to know their names, obviously, body-centered and face-centered. Okay. And we need to know the difference between them. And what is the difference between them? Well, basically, this one repeats every other layer, and this one repeats every 3 layers. So the difference between is, and I almost am just asking you to just memorize this, which I hate, but you know, this is a pretty complicated geometric investigation that's really beyond what we're doing. You just need to know these terms, and I want you to know the difference, okay? So just memorize this, please. It's going to be a question. One repeats every other layer, and one repeats every third layer. Okay? So just when I say repeats, I mean that this layer is directly on top of this direction, directly on top of this first layer. Whereas this guy, you see these green ones line up identically with the blue ones on not the layer below, but the one below that. So every other layer is back where the first one started. Okay, and in this one it takes 3 for it to get back. Okay, that's it. You need to know that electrons are delocalized in metallic bonding. Okay, and that metals have what? High thermal conductivity, conduct a lot of heat very easily, and high electrical conductivity, that conduct things very easily. Okay, and that's because of those shared electron domains. Okay, I don't have a good metaphor for that, so I'm sorry. Just know that it's shared electron domains. They all overlap and they all share. Okay, just still think that fact right there is really cool about the color of copper being the exact wavelength. All right, so we then have, bonding forces, ionic and covalent. Okay, and then we have intermolecular. And if we were going to be like super symmetrical, we could call this what? Intramolecular. Within the molecules. Okay. And inter is between molecules. Okay, so we've got our little okay, so we often that's represented like a little dotted line right there between the guys. Okay, it's like a semi-bond. Okay, guys, this is just a little plug here. If you didn't go back and watch, I think we had a couple of people who were out over the last week. Make sure you go back and watch those videos. I know kind of seems like a big chunk of time, but it can help you get ready for this quiz and just kind of be back in the groove of chemistry if you missed those. Okay. So intermolecular forces, what do we have? We've got hydrogen bonding, which we'll talk more about in a second. You guys should be super familiar with because of the Asimov thing y'all just discussed. And then the van der Waals forces. And that should actually be 3 separate words. But you got it. Okay? So right here he contrasts the Bond energy is here, 2200 kilojoules per mole. The actual numbers are not that important. See that an ionic bond there is the strongest, because remember this is how much energy it takes to break them, which is a measure of their strength. Okay, and then this is one, between a third and a fourth of that. So covalent, it's ionic, and then covalent. All right, and then we have the hydrogen bond, which is about a tenth of a covalent bond. Okay, and then you see that the van der Waals are about a tenth of that, or even less. Okay. All right. So if we look at this, I would not be surprised if something like this were on there and I asked you to label the sigma positive and sigma minus, negative. Okay. And what are those? Those are our partial positive and negatives. And so we'll call those sigma positive, sigma negative. Okay, and where those show up. Remember, O is the electronegative one, and he's got the lone pairs hanging out there, so a lot of negativity right here, real downer to party. Okay, and what does that do? That moves these electron clouds this way a little bit, creating a partial positive space right here. Okay, so of course those are attracted now. And that is where that hydrogen bond ends up forming. That hydrogen is semi-exposed as a proton because those electrons have been moved away, and then it's very attracted to the negative in another guy. Okay, and that's what we end up seeing right here with this dotted line, which is the hydrogen bond. And as you guys learned, and just discussed in the Asimov thing, like that's enough to add 80 degrees to its boiling point because those molecules are so sticky. You have to add all that heat into there to break those hydrogen bonds and turn that liquid water into a gas, which again, as you learned in the Asimov thing, was super important in how the Earth functions, which is fantastic. And I told you Asimov was super snarky about that. I think I said that in the little PDF there, but golly, how is that not just fantastically orchestrated and designed? I can't help but just think that's amazing. So, all right, hydrogen bonding, you need to know its relative strength. This is the strongest of the intermolecular, okay? It's the strongest of the intermolecular bonds. All right, then we move on to the little weak guys here, which are our van der Waals. Okay, and you need to know Keesum, Debbie. Did anybody look that up? Dubai, Debbie. And then the London dispersion. Okay, and they have this helpful little thing right here that should help you get straight on what they are. Okay, remember we need to know what a dipole is. Guess what? It's something with two poles. Pretty amazing. And of course there are permanent and temporary. Okay. All right, and so notice how similar these two are. Okay, so a water molecule is a permanent dipole. Okay, it's a permanent dipole. It's got a positive area and a negative area. Those are poles. Okay, and they're strong poles. Okay, but notice that this is the hydrogen bonding that happens only between a hydrogen and an oxygen, nitrogen, or fluorine. One of those very electronegative atoms. Okay, so that's a specific kind of bond. Okay, now this is a force between any other two permanent dipoles. Okay, so that's an attractive force. Okay, and then just like a magnet can sometimes cause other things to act like magnets, a dipole coming into an area can force those charges to be segregated, which means that it starts acting like a dipole, and then that's also an attractive force. Okay, and then finally you got the London dispersion ones, and that's just where these electrons are kind of zipping around, forming like accidental dipoles every once in a while. You know, broken clock right twice a day, atom is dipole twice a day, and when that happens, they, you know, attract and repel depending on what's going on. And because it's so random, and because it's not all of them all at one time, that's generally a very, very weak force, and really doesn't do a whole lot other than explain a couple of weird behaviors that substances occasionally do. Okay, we need to know what they are so we can be familiar with them. All right, so again, what do we do? Bonding forces, electrostatic or ionic, right? And then we got covalent. You know that. Then you need the intermolecular forces are these two kinds, and under this under the van der Waals, there are these. And I'm sorry, they're all, you know, formal names. I wish that was not the case, and they were just named something that's super intuitive, but they're not. Okay, so you've got 2 days, make some flashcards, be able to do them, be able to label them. It may be matching. I may draw it and ask you to label it. I don't know. There's just some stuff in here that you're just going to have to memorize. Okay, not my favorite, not y'all's favorite, but there it is. Sometimes the world just doesn't cooperate with our desires. Okay, so I think you know pretty clearly what's going to be on there. Like I said, I'll be writing that over the next couple of days and get that to you on Thursday. And then after we take the quiz on Thursday, we're going to move into Chapter 7, which is another really meaty chapter, as it were. Sorry for all you vegetarians out there. It's a very heavy chapter. Got a lot of really central chemistry concepts. We saw that in Chapter 5, where we were just kind of plowing through a lot of material all in one chapter. Well, we're about to do that again here. So we're going to take our time. We're going to move through it. And then after we get done with Chapter 7, we're probably going to do another lab that's really focused on some of these concepts, because I think we can do some of these in a way that's fairly straightforward, fairly simple, and hopefully it doesn't blow up at all. That's always important. But we'll get there when we get there. So come in prepared for that quiz. You know, put in the time. You shouldn't be surprised by anything on there. And just, you know, let's knock it out. Let's move on to Chapter 7 and get moving into that. Okay. All right, guys. Email me with any questions, comments. Actually, you know what? Just don't send me any comments. Just any questions you might have. All right. I'll talk to y'all soon. Thanks.